All right, guys. Yeah, I'm hoping you can hear me right now. I think I'll be taking the session on Intro to Rust today. It'll be a very beginner-centric session in the sense that I'm targeting this towards users who want to jump into Rust. They're not exactly very comfortable with Rust per se, but they are sort of they're like they know what language it is and what programming is. So that's sort of my goal towards this session is. And I think we're ready to get started. So, yep, the first, the first step, like in your journey, is like you want to sort of install Rust, right? So have this link up on my PPT, and I think like there should be the link should be in the chat box in about some time. Uh, this is the link. This is a sort of the link that you need to visit to sort of install Rust on your system, right? So if you visit this link, I have it pulled up already, right? This is a very comprehensive guide on how you want to install, right? There's certain commands if you're on a different system, like if you're on Linux or Mac. I'm on Mac right now, right? So you're supposed to use these commands, right? And if you sort of look at this is a very comprehensive guide, right, which goes in depth on Rust, and like it is exhaustive in the sense that this has more or less all of the things that you need to know Rust or when you use this language. So this is the sort of the so we're going to sort of not cover all of this, but this is a very good reference for you in either case. Like if you're confused about any concept that you might encounter, like when you're looking at the language. So yeah, so if you're using Linux, you're supposed to enter these commands in your terminal, right? On macOS, you might have to get this as well. On Windows, it's a bit more difficult. You'll need to sort of follow these instructions, right? I'm on Mac, I won't need to do this. And like if you're like done with everything, right, you can fire this command in your terminal window, right? So let's say if I have my terminal open, uh, right, we'll open a new terminal. So you can fire this Rust C version. You see, I have the 1.73 version of the Rust compiler, right? And similar, you'll have different instructions for macOS as well. And then this is updation and documentation is fine. So okay, so coming back to topic that we have here. So what I'll be using when I sort of let's say take this session, I'll be using VS Code, and there's this very good extension for Rust on it called Rust Analyzer, right? It does a lot of cool things. I'll sort of show you like when we go towards the more interactive part of the session. And yeah, and so that's so how you sort of get started with it is you enter this command in your terminal, right? So if you have cargo new, whatever you want to call it, right? So if you have session, like example, so it's created a binary, right? So it creates a directory, right? And you'll sorry we'll just do normal ls. It'll have an src directory and a cargo.toml file. So I've already sort of created uh, a project, and I've opened it in VS Code so we can sort of see it a bit properly. So what you have is you won't really have this directory that's just created when I opened it in a different editor. Yeah, so you'll have basically the src folder and the cargo.toml and the cargo.log file. So this is basically the file where you specify your dependency and the information about your package or your crate, right? So these are sort of terms I'll explain a bit further along. But what you need to know is that cargo is the manager, like the package manager for Rust. It manages all your Rust files and sort of let's say provides an environment for you to execute it. So that's sort of cargo, and then Rust C is the compiler. When you have Java, you have Java C. So you have similar when you have a Rust C, right? So going to the main files, so all Rust files end with .rs. That's the extension that you need. This is created by default, right? You'll have this sort of a everything already there if you execute these commands. So what you can just first see is that there's this println, like print line, right, which you might see in a lot of other languages. This sort of prints everything in the, like, prints the arguments to the output. So if you want to run a cargo crate, then you use cargo run, right? So it builds your crate. So there's like 2-3 steps here. I won't go too in depth in it because it's sort of besides the point. But it compiles your program, it assembles it, links it as well. And because this is the debug version, you will also get some debug symbols in the what do you say, in the binary, and it then executes it. So if I run it again, I don't get the compiling step because it's already compiled and there's no difference in between the files. So that's quite smart about it, right? So this is sort of the intro. So this is the section, right? And now we'll sort of jump on to the usual stuff. Like, as you see in all of languages, you have data types, you have variables, you have, functions, right? That you have basically in every language, right? So we'll sort of go ahead with data types, right? So you have types that, scalar types, so you can hold one type of value, right? So if you have, we'll just erase this, right? And just as an aside, right, this is a macro, right? It's not exactly a Rust. Anything that ends with an exclamation mark is a macro, right? So a macro is something that's evaluated at compile time rather than runtime, like normal code is. So I'll explain that a bit later, but you have to understand that it basically just prints it to the standard output. That's sort of the object of the statement. So I'll comment it, right? And when you say you have data types, you have your integers and your floats, right? So in the Rust, you have multiple integer types. Uh, you have so we'll sort of, yeah. So these are the types that you have. You have a U16. The U16 stands for an unsigned integer type of 16 bits. So the width of so the amount of memory it occupies in, like, the amount of memory it occupies is 16 bits. That's 2 bytes. So you have U16, you have U8, which is just 1 byte, and you have U32, and you have U64, right? So these are the 4 unsigned. So when you say unsigned, there's no sign to the number. So you can represent numbers from 0 to some, n, depending on the amount of bits you have, right? 2 raised to n minus 1. Yeah. And so you can't represent negative numbers. Now, on the other hand, you have I types. So these are the signed types, right? So these are the integer, sort of the signed integer types. So these can represent negative numbers, but they have half the sort of maximum value that you can hold in a normal unsigned. That they hold half of it. So you have minus 2 raised to n by 2 minus 1 to minus 2 raised to n minus 1. So that's sort of the, yeah, that's the capacity. Then you have the floats. So these hold floating point numbers. So again, you have float 32, float 64. So those are your types. So those are scalar types. You also have strings, right? So let's say you have, this is some piece of Rust code I'm typing out, right? So, wait, you can't do it this way. Wait, look, my bad. So yeah, so what this creates, so this is sort of the nifty. So there's a lot of things happening in this paper. I'll break it down one by one, right? So I've sort of skipped ahead a bit. This is also how you define a variable, right? And here you have the type of the string type. It's a scalar type, and you can see it's a UTF-8 encoded global string, right? So those are the ones that you'll use for sort of all your common string operations. Yeah. So those are the string types, right? And now, so this is a syntax I'll come to a bit later, but this is basically created a variable. So let and the cons I'll come to like the next slide over, but sort of just bear with me a bit here. So that's our scalar types. The next we have is a compound type, like an array or a tuple. So let's create another variable. Oh, right. You have 1, 2, 3. So I've created an array of 3 numbers with values 1, 2, and 3, and it's given the type integer 32 bits wide and with 3. So this is the sort of syntax that you'll need. This is the sort of type of this variable O, right? So there's another nifty thing in Rust that you don't need to actually specify the type. You have a lot something called a type inference, right? So the Rust compiler is smart enough to figure out that if I have let O equals to, in this sort of syntax, I must mean it's an array of integers, 32 bits wide, and there's 3 of them. So that's the default that is assigned. If I wanted to, change the types, right? If I do 1.0, it's become F64, right? So it's now floating point number with 64 bits. So that's sort of the thing. And now you have tuples. So the important thing about arrays is, which is like any arrays like in other languages, that you can only have it be of one type, right? So if I have, so this, so this is allowed, and this is also allowed, but you can't have anything in between them. Like the compiler will try to coerce it into one of the other types, but you generally can't. So it has to be of a singular type, right? Because Rust is a statically typed language. The compiler has to know the types and the sizes of all the variables that you use at all times, right? So like at least those that are on the stack. So like those that are compile time defined. That's it. And now you have user. So okay, wait, you have tuples as well. Didn't forget. So tuples, for example, can be of multiple types. You can have like you can have any number of sort of things here, right? There are multiple types, and they're sort of it's a tuple. So like if you come from Python background, then you know what a tuple is. Basically operates in a similar way, right? And now we have user defined types, right? So the syntax for the user defined types here is, if you have a struct is a collection of types, right? And an enum in the enumerated values. We'll come to this in a bit, but basically it's a collection of types, and this is like, so if you have struct A, right, then I can have members. If you have come from a C background, you know what a struct is. If you come from a Java background, it's similar to, let's say, a class, right? So you have red being a member, which is of type U32, and blue could be F64. So this is sort of the syntax for it, right? Okay, so there's some special types as well, which I won't discuss now, because you never sort of come across it in a normal execution, but you need to know it exists. The never type and the unit type. The unit type is the one, let's say, is sort of no type. So this becomes a type. This is the unit type, right? And the never type is used to define computation that never sort of comes out. So if you have, let's say, an infinite loop, right? So this has a type of never. So this statement will have the never type, because this loop never because this loop never ends. So we'll come to this again. Like I will revisit these examples again. This result and options are very important types that you'll see a lot if whenever you're practically using Rust, and that's because of the nature of null handling in Rust. In the sense that there isn't any null, like there you can't have null values, right? So if you have, let's say, just let O, right? So if I remove this, right, if I don't assign it a value, and I try to let's say print O, so it shows a red squiggle, right? So you need to give it an explicit type. So because when you have a type may have a default value, so it might sort of coerce from there, right? So if you run this, you need to give it a type, and you need to have it be a value. That's sort of the logic here, right? So okay, so we'll come to variables now, right? So like I've sort of already like created a variable, so you can declare a variable let or a const, right? So if you have let O is 2, so I've created a variable called O, right? Or you can have const n equals to 5, right? Yep. So That's sort of the nature of it. So const needs to have an explicit type while let's don't, because consts are supposed to be a constant in code. So you need to give it a type. Let's, I can give it, let's say u32. Yep. Now, so coming to the second point, mutability is explicit. And this means that not variables are not mutable by default, right? So you have O. So if I give this statement O equals to O plus 4, this is an error, right? You can't mutate an immutable variable. So for you to do it, you have to declare it mute by using, mutable by using the mute keyword. So I have let mute O, right? And then suddenly it's gone away. So there's again some other linting warning, but it's fine. So this is valid trust code. This will run. Yeah, then we didn't print anything out, right? But this runs, right? So we already covered they need to have specific data type. The compiler can infer types. So in this case, it has inferred the I32 type, but they all have types, right? And then you have this another point that says can be shadowed. What does variable shadowing mean? So variable shadowing means you have, let's say, so I have O, I've already defined the O variable, right, as I32, right? So I can redeclare O, right, and have it be a different type. So now from this point of execution onwards, O refers to the F64 variable, not the I32. So that sort of, replace the variable with a new one if you want to look at it that way, right? And now if you try to mutate O again, it doesn't know, because now in your second shadowed definition of O, you haven't made it mutable. So that's sort of the rounding of that. So again, you can't have null variables, as we said, right? So you have let mute O. Let's give it. Sorry. Let's give it. Yep. So right now I'm not using it, so it's fine. But now if I want to print this variable out, it's not X. Sorry, O. So it gives me an error immediately. O isn't initialized, so you have to give it some sort of a value. You might have a default value or so on, right? So now function. So now as I've sort of not explained this, but this is a function, right? Fn main. So this is, you declare functions with the fn keyword, right? The main function is special. This is the point of execution of all Rust programs. So everything starts with main as such. So you have main doesn't really have an input or an output, but you can define your own functions, right? So you can have fn do something, right? And I can have it print hey. And if I wanted to execute this function, I would call this function in my main function by using this. And if I ran this, you get hey, right? So this is sort of like, this is the function. So then you can have any number of inputs, right? So I can input anything here. Let's say function do something. You have an input, right? And you have an output. So this is how you declare. So if you have an input, you declare variable colon type. And again, you have variable colon type. So this is sort of the format for it. And then for an output, you would use it defined with this arrow mark here, right? And let's say this defines the return type. So you need to return something. So if you save it now, you get an error because it sort of expected the U32 type. So we'll sort it by using A plus B. Right. There you go. And I need to provide some arguments here as well, right? For file, let's do this. Obviously we didn't print it, so you're able to execute this function as well. Let's print this value as well. So you can see I don't need to sort of define the type here, right? This is annotated by VS Code. So I can do this. Yep, there you go. Hello world 9. So it sort of added the function together. There's something known as associated functions, right? So when I was doing this, what do you say? String new. right? So this created a new string. What this is, this new is an associated function defined on the type of string, right? I'll go in depth in associated function when we do structs, right? So right now you need to know that you can assign functions to types and or instance members or variables, right? So this is sort of the string type. Uh, so now, okay, have you here? So structs and enums, right? So structs are a collection of type, like in the example earlier, we'll go with this struct, let's say pair, right? You'll have the first member be a string and the second member be, let's say, an F32, right? Now, so this behavior or implementation, as I was saying, is the associated functions. So to define an associated function or an implementation or a behavior, right? You're supposed to type out the IMPL keyword, right? The IMPL block, and you go IMPL pair, right? So you IMPL and the name of the stock you want to define the behavior on, right? And then you can define functions on it. So you have fn new, for example, right? Let's have this return a pair, right? So as we discussed earlier, the struct itself is also a type. So function can return a type of, sorry, a function can return a value of type pair, right? So how you instantiate a struct is by using this syntax, right? So the struct name and curly braces and then the variable name. Let's use the predefined function on the string type. Like, so this string new is defined much in the same way as our pair new. Like, it does a bit more as well. So even F32 has associated function, as you can see here, right? So you have absolute, acos, whatever. So you have a default F32. I think it returns a 0. Yep. So there you go. So see, as you can see, there's an associated function in this implementation, right? So this is, so if I wanted to call this, right, function, I would say let's say my pair new. So this double colon operator is sort of the scoping operator in the Rust. You sort of scope into packages, structures, types, by using this operator, right? And now if I wanted to access my pair's members, over to my pair dot first would give me the first string, and my pair dot second would give me the F64 value. So now just for let's just to just for curiosity, we'll print out the values in uh, in my pair, right? So this syntax is what you use to sort of print, sort of to use, you wanted, if you want to convert strings or let's say variables, if you wanted to convert them into, you wanted to print them or format them, you sort of use this curly braces to sort of inject the variable into it. So the first curly braces will correspond to this value, and the second one corresponds to this. Right? So if I run this now, you get hello world. So this the string new is a default one, right? It's an empty string, so there's nothing here, and the F32 is a default 0. So you have this here. Okay, so think about struct. Now, okay, enums. Enums are a bit more exciting in the sense that enums do a bit more in Rust. Typically, an enum is a type which can have a specific number of values, right? So if you, let's say if you have a classic, enum, I'll remove this. Well, I'll keep it there. Go down. If you have enum, colors, the classic example, right? You can have a type of red, maybe blue, maybe green, right? And then you can have a variable let call equals to color. So again, you have scoped into this enum by using uh, the double colon operator, right? So when you want to refer to, let's say, a specific types of an enum or such, you use the scoping operator, right? Now, so again, you have a type with a fixed number of values. So your color can be red, blue, or green. You can't have anything other than that, right? Now the twist here is that that an enum variant can have member types as well. So let's say if I wanted to support tomorrow, I wanted to support more color. I don't want to support just red, blue, and green. So I can have a custom color, right? Which could, for example, take in no, we'll do the RGB, we'll do it in RGB format, right? So you have view 32, 32, 32, right? So now if I wanted to have a let custom color, or let's say let black. So we can have color custom 255. No, this is white. Sorry, my bad. So yes, black is 0, white is the full one. Okay, yeah. So this is also a valid syntax. So every variant can carry types in itself as well. So there you go. Yes, and enums can also have implementations. So I can have implementation of color, right? Let's say if I want to provide a new implementation. Let's say every a new color can always be let's say blue, for example, right? So there you go. This is valid Rust. I'll add in the return because I want to explain something else later, right? So this is return, right? So then, as you've seen, you can also have enums as a type, so they can also be a parameter to a function and all. So whatever, maybe, yeah. So there you go. Now we'll come to control flow, right? So control flow is sort of so we'll cover if else and loops. There are a bit more, let's say, advanced constructs, right, which I won't be covering today because they require a little bit of a jump. But we'll stick with if else and loops. They're very good enough to do what most people want, right? So if else works as expected, right? If I have, let's say, if call equals to color red, you want to print call is red. Okay, that makes sense. You can't do this because you have to derive an implementation of EQ. Yeah, okay. I'll explain this in a bit, right? These are all macros as well. They generate implementations for operators. So every operator in Rust has to have a backing function. So let's say it's already highlighted by VS Code here, right? So when you use this double equal to operator, Rust internally calls a function known as EQ, like function EQ defined on the type. So if you want to compare, let's say if you wanted to compare two values of a single type, right, then you need to have an EQ function defined on it. The EQ function is already defined for, let's say, let's say normal types. So if you have, let's say, if 2 equals to 3, so they'd both be I64. So you have, sorry, they'd both be I32s. So you already have an I32 defined. So you already have an EQ defined on the I32, uh, on the I32 structure, on the type, sorry. So we'll do, let's say, let x equals to 2 and let y equals to 4. So if you have y greater than x, then you can say y is more, right? Else if y less than x, you have y is less, else they are equal. This is sort of the syntax that we use for if else blocks, right? So you have y is more, what do you expect? So you give if, and then your condition, there's no need to have a parenthesis around it, and then these curly braces, right? So like I said, anything that evaluates to a Boolean value can be a condition. So the EQ function, or even this is represented by the greater than function. So this is the function on screen. So even that uh, is represented by a function. So that returns a Boolean. So If it's true, it executes. If it's not, it goes to the else if block. Like, like it works as expected. Yeah. So this is sort of the, let's say, a key point in Rust, which I included a bit late, right? So every statement in Rust returns something, right? So uh, let's say if I wanted to, right? Let's say if I have let if block, if I create a variable. So this is valid Rust code, right? Because even every statement in Rust has a return value. So even the println macro also has a return value. Even so, if I sort of remove this, right? So these sort of return so the return value of a block statement, for example, is the return value of the last statement. So if I have 2 here, right, is incorrect because it expects all branches to have the same. So like I said, it expects all branches to have the same types. So if I have 0, 1. So this is valid Rust code. Now, so now the value of the if block depends on what branch of the if statement executes. So if I now print a value of if block, it's 0 because it executed this branch. So it executed the statement, right? And because we put the semicolon, it forgets that sort of it doesn't return that value, and then it goes to the last statement, executes it. The return value of the last statement is itself. So then it assigns that to the block. So in the same vein, right? If you have a new function, right? So if I do this, this will still work. This like it still returns color of blue. And this is why this also works here. So you're returning a pair, right? There you go. So again, so unless you terminate a statement by the semicolon, it returns the unit type. That's why the special type is a unit type that it represents nothing basically. So now loop, yeah, here you go. We're coming to loop now. I already showed you a bit of a bit of loops earlier. So you have mainly 3 types of loops. You have the loop. This is the unconditional loop, right? So if I have tell an A is D, right? This will never stop to execute. So if I run this, see, infinite, right? And incidentally, this is also where the never type is used. So if I have a function, infinite, it represented by the exclamation point, it represents computation that don't end. So the return type of this function is the never type. So if I have a variable here, it has a never type. So there you go. So if I still run this again, still infinite. That's the other special type. There are then plenty of other types in Rust. We won't be covering a lot of them here, right? And there you go. So it's the first type of loop. And now you have, let's say, the for loop, right? That's the most classic one. So you have for variable in let's say, so here the definition of what you can put in this is quite, let's say, quite vast. It's anything that can be coerced into an sorry anything that can be coerced into like anything that implements the iter trait, right? So what that means is I'll sort of explain it a bit later, but basically stuff like this works, right? There's a lot of, let's say, witchcraft going on. Again, this is not the never type because you can't see it. Again, you want the never type, but you found a unit type, so this is the wrong definition for it. This will work, right? So 1, 2, and 3. So this it goes from includes the first field or include the last variable. So it works on arrays as well. So if you have, let's say, an array 1, 2, 3, this will also work because arrays, and in this case it iterates to every element, not just the one, but like that would be silly otherwise, right? There you go. And then you have the while loop. So the while sort of works like usual. So while and what you can put anything, any condition in here that might evaluate to true or false, and you have this. So the compiler is warning me here is that infinite loop, it's an infinite loop. So you wanted to denote them with the loop, not don't with the while loop, right? So yep, there you go. Okay, so now we'll move on to ownership. This is one of the more trickier topics in Rust, and that's because it's not tricky to understand, it's tricky to use. Let's put it this way, because at the end of the day, you don't want to sort of learn the language for the sake of it. You want to do something with it, right? So ownership, broadly speaking, is like one of the, like, it always feels like the compiler sort of holding you back, and a lot of it's because of this concept, but it's not the case. It's just, I'll sort of explain more, right? So ownership, we'll get to ownership right now. Yeah, yeah, I think pair is a good one for it. Let p equals to pair new. Okay, so this is a very standard. Let's say forget about all of this here, and I'm moving this off screen so you don't see it. Okay, so you have this, right? Let p equals to pair is equals to new pair, right? Now, if I wanted to print, let's say uh, p dot second, I get 0, correct? Now, let's say make it mutable, right? And now I changed the p dot second value to 5.0. We have 5, right? So this works as expected. Now let's throw a twist in here. Let's do let y2 equals to p, and suddenly is this won't work anymore, right? You couldn't compile it, and if you look at the error, like Rust has extremely good like error reporting in this, and it's very clear. Like a terminal itself can tell you a lot. So you have the error basically is here, borrow of moved value p dot second. So what does this mean? So it means that every variable owns a value, right? So when and only one particular variable can own a value at any one time. So when you sort of do this when you assign a variable to a variable, the ownership of the value behind the variable. So when you do let y2 equals to, so when you first let p equals to a new pair, right? The value, the new pair value, right? Uh, it was owned by p, and now when I did let y2 equals to p, the ownership of the of the new pair transferred onto y2. So now the variable p is no longer valid. That's sort of the concept behind ownership. You can only sort of use owned. You can't only use owned values. A value can only be owned by one variable at a time. That's sort of, so if I now use let y2 dot second, this is valid Rust code. This will work. So you see that you sort of consider the variable p to be not dead after this point on, right? You can't use p anymore. This sort of the logic behind this. So so when you say, yeah, so ownership moves, right? Functions take ownership of the area it takes as an input. That's sort of the third point we did first into. We'll come to the third point. So if you have, let's say, a function, okay, I'll do this example with a string because that's sort of a bit more easier to say it out loud. String from SD, right? And we'll do this. You have fn do something input p, so input string. Now we'll just have this function do anything, right? Println hey. Now if I call do something with p, I again can't use p here anymore. If I wanted to print p out, this is an error because again it says the borrow of mode. So the value of p has again moved into the function. If I wanted, let's say, to use this value again, I can return it from the function. So let p2, and this is fine. So you have sort of, so the function takes in ownership of whatever it sort of takes in as an input, and it yields ownership of whatever the output is. That's the logic behind it. And yeah. So okay, so that's something. Now let's come to copy type. So string is not a copy type. That's why I was using this example with string. If I, let's say if I did this with an integer type, right? And I32. So this will still work. Why this works is because the integer, the I32 is a copy type. So whenever a variable, whenever a variable is represented whenever a variable is marked as a copy, whenever it moves, a copy of it is made. So if I mutate the variable, let's say, let's assume that this is not the case. Let's not, let's not do this. We'll do input equals to input plus 3. So if to mark it as mutable, right? So it's warning me that there is no, like it's a valid warning, but there's a demo here, right? So even though that I added the 3 to it, it didn't reflect outside. That's because it's copied whenever it goes into a function. That's what a copy type means. So whenever you have reference type like a string doesn't sort of, it owns the data it refers, but it doesn't contain the data. So whenever you pass a string in or you assign a string, it doesn't copy the internal contents because that's explicit behavior. That's sort of the logic behind it, right? So that's why I said copy types aren't usually bothered by this. Now again, so this is sort of a very annoying thing to work around, right? You don't want to sort of do this pattern over and over. If I wanted to, actually mutate an integer, I don't I don't want it to, keep returning it. That's silly, right? And then I would have to shadow it again to actually get this to work the way it's supposed to, right? I had to define the variable, I had to move it in the function, and then I had to sort of shadow the variable again and then print it out. And in the function, it's even more unclear. So it doesn't sort of make sense, right? So then we can come to borrowing. Now, you can sort of borrow a variable by creating a reference, right? So what a reference is references are like basically pointers, but they have certain constraints, right? A reference can't be dangling. So people who come from C are well aware of dangling pointers, where you have a pointer to a particular value, but the value itself is invalid, has been destroyed, or is not, basically is not in scope, or like is not, you've already zeroed it or something, right? So you have dangling pointers. So pointers exist, but the value doesn't exist. That's sort of an issue. So this is always checked or enforced by the compiler, right? So you can't have dangling references. And again, a reference, the even the mutability of a reference has to be explicit. So you have to mark a reference as mutable for it to actually change whatever is behind, whatever is referred to by that reference. And yeah, there's like this 6 point I'll explain by using a demo, right? So we'll come back to, we'll use a string here again, because I thought it was a copy type. String from, right? So instead of do something, so you have input, right? So we'll not actually, we'll use this now, right? So there isn't anything here. Okay, so we'll examine this now, right? We have created a string in the first line, right? And now passing in a reference to string, and when you pass in the reference to it, the ownership of the original variable doesn't change. So if I have, let's say, let p2 to and p, the type of p2 is a reference of, a reference of string. It's not a string itself, right? So if you pass in P2, right, this is fine. A reference is also like copy type, so I can do this multiple times. So this is also fine. And I haven't technically lost ownership of P because I never passed in P, right? So if you run this, so again, so you passed in the value of input into the function without losing ownership of it, right? Now, what if you wanted to mutate that variable, right? So right now this, so if I wanted to, let's say, so this isn't allowed because it's behind a shared reference or an immutable reference. So for you to be able to change this, you have to make it a mutable reference, and now this works, right? So again, for a reference to be mutable, you have to make the original variable as well mutable. So now this will work. Yep. Now another interesting case is this is not allowed. You can't have an immutable borrow when you already have a mutable borrow in in scope. Like you can't do that. And that's sort of the sort of two constraints of references. Like you can have either an infinite number of immutable borrows, or and shared references, or you can have one mutable reference. That's it. You can't have both of them, right? So even this is not allowed. Yep. So that's sort of the reason behind it. And yeah, so I'll sort of now explain a bit more. Is that the thing that sort of checks all of this, whether all references are valid, that they're in scope, is the value behind it still valid, is it destroyed, is it so that's all of that is done by the borrow checker. That's sort of the it's a compile, basically it runs at compile time, it enforces these guarantees at compile time. There's no all of this doesn't happen at runtime, it happens at compile time. So if those rules aren't followed, your program doesn't compile at all. So that's sort of the reasoning behind it, right? So another thing is that references will always be active as long as the backing value is active. So if you have, let's say, references can't outlive the original value. That's sort of the meaning behind it. And you can't modify the original value when the reference is active. Is like if you have, let's say, if you have and p, let's say, this isn't allowed because, oh, right, sorry. Uh, so it expects the string dereferences too. Sorry. So this will throw an error at runtime, right? So there you go. So I'll now explain sort of the purpose of ownership rules, right? Is the fact that the purpose of ownership rules is basically that you want to have fearless concurrency. Right? A problem in concurrent, let's say, a problem in concurrent applications are that you have, let's say, two things trying to write to a same value in memory, right? Two threads, data races, all of that sort of starts off from the fact that from the fact that you can have two independent processes modify a single value, right? So a common way to tackle concurrency issues is the single writer principle, which is what the mutable reference sort of enforces, is the fact that you can only at most have one writer to a value. So you'll never have data races. You'll never have, let's say a double free, right? That's what used to be a very infamous problem in C. Like when you would free a variable, free memory two times. It's undefined behavior, right? So that's sort of the logic behind this, right? So now we'll come to results and options. These are two, let's say, enums, right? And they're sort of very important in Rust in the sense that you'll be working with them a lot, right? So we'll do option first, right? So we've already explained that a variable has to have some value, right? You can't have a variable that doesn't have a value if you want to use it, right? So a common way to go around it is to use the option type. So you have sum of, let's say, 2. So an option type is just a generic type, right? So if you look at the option, this is the source code for option. Like you can ignore all of these hash derives and all that. They're used, they're macros, and they're used for either marking stuff or annotating stuff. So this is you can ignore it right now. So you can see that there's an option has two variants, either it has none or it has some of some types, an option of t. So you have an option of I32, for example, in our example, will have either a sum of some integer or no or none. That's the logic behind it. So if you have, let's say, so I can, so this is sort of so if you have, let's say, a function that may return no value, if you have, let's say, if you have some function option of I32, right? So in, let's say, in a different sort of a paradigm, right? Let's say if you're coming from a Java background, you might always return null types, right? If you wanted to signify that there is nothing to return, you would return null, right? Or you would, let's say, that's sort of, if you have, so that's sort of the alternative is to use the option type, in the sense that you actually signal none explicitly rather than saying it's just null and letting everything handle itself. So let's say if you have, let p equals to some function, right? That's sort of the logic behind it. And then you have associate functions on the option, right? So if you do p dot, you'll have your functions like is sum, right? Which, so it returns true if the option is of a sum variant, right? And then you have options dot is none, right? Which returns if the option is a none value. And then you have, let's say, is sum, right? And then you could have let y equals to p dot unwrap, right? So what unwrap does is it consumes the option and it returns the, what do you say? It returns the inward value, and if it's a non-variant, it causes a runtime panic. A runtime panic is something that sort of ends through, right? It's an unnatural state, and you're not supposed to sort of, you know, let's say you're not supposed to. Typically, it's in an actual application, you don't really want to panic. Panics is basically used for unrecoverable errors. It's when something's really, really gone wrong, right? So in most cases, whenever you have, let's say, a null value, you might have a default value, right? So you have unwrap, or let's say let's say either you have an I30, if you have an option of some number, or if you have no number, then it might just be 0, right? So then you can sort of do this, right? Wait. So if I execute this code right now, you have, yep, there you go, right? So you can, so even though I returned none, right? So the unwrap failed and we got the default value out. So if I now return sum of some other 5 value, sum of some other value, then you have 5. That's sort, there you go. Now I'd like to explain, I'd like to sort of so there's sometimes when you're sort of relying on some other inner function, right? If you have fn some inner function which also returns an option. So let's say if it returns an option of u32, right? Now if that function returns none and you're calling the function here, right? If your function depends on some other function for some computation, and if that returns null, then you also want to return null, right? And like if that's sort of your use case, then you can just sort of use the question mark operator. The question mark, oh wait, the question mark operator sort of causes early execution of early return from a function. So let's say to demonstrate what the question mark operator does, right? So we'll have this sum of two, right? Now here the sum function calls the sum in a function, right? And it has the question mark operator. So what this does is basically it if the value is of the sum variant, it consumes the value and returns the inner value, or if it's the none, it causes an early return. So whenever you have so so in this sort of case, you will never see this hey being printed, right? If I run this now, so you just see zero. Now if I return some value from here, see, so we returned this hey and we returned sum of two, which is unwrapped here, and it printed two. That's sort of the logic behind option, right? And now you have the result type, right? The result is useful when you have, let's say, an explicit error that you want to return back. Let's assume that you have uh, let's assume that instead of we'll first take a look at the result type, right? So result also is an enum. It has two variables. It can either be an OK of type T, so it's generic, right, and an error of type E. So there's sort of the two variants of it, and we have different functions defined on the results as well. So we'll do a use case here. So now uh, let's assume this returns an error, and let's assume that zero is the error code. When you have to have more explicit, let's say, results that you want the computation to either succeed or fail with some value, right? You don't want it to also just be either a result or nothing, right? So we have this, right? So result r32 ru32, and let's say our function add is the add, right? It calls the first value, it calls the second value, right? Sum in a function, right? and it and it returns, and it's supposed to, let's say, return the sum of these two, right? We'll unwrap this just for demonstration purposes, right? So if add, right? So the unwrap part also does the same thing. It's similar to the option where if you have an OK variant, it consumes the result and then returns the OK value, right? So if I execute this now, I have zero because I'm returning an error type, right? If I return a variant of, let's say, 4, then I have 8, right? Now let's assume that if any of these are of an error variant, right? I also want to return an error, so we can do it in this way. I wanted to propagate the error back up to the caller. I don't want to unwrap it. I want to let the caller handle it, right? Because so this question mark operator can also work in this way. If you have results of similar types, it returns the result up to the caller, and then you can then you can sort of, the caller can handle the results. So that's what the caller is doing right now. It's unwrapping it, right? So instead of just this, we'll print P directly, right? So sum enough, we'll have two of these to demonstrate the control flow of the results. So we'll have the first one return an OK option of 2, and the second one return 3. If you run, you'll get 5, right? Now, if I let's say do this, right? And if I return an error from the first variant, I have an error type. I never printed hey or hey2, right? That's because the function that the control returned from here because it returned an error type and propagated the error back to the caller, right? And now if I sort of turn it around, I I executed this function, got an OK value, printed hey, tried to get the second value, but the unwrap failed and it propagated the error back to the caller. That's sort of the logic behind this results, right? You will see a lot of these chained across an actual code base. So again, as we see, we explain the question mark operator here, right? So you have, you can, so all of this can also be done with, functional programming style, functional programming style, right? So let's say if I have the first one returns an option and the second one returns an error, right? So then I can convert this into an error using the OKR function. Sorry. Yeah, to is 32. Wait. So there you go. So I've converted the option into an error. So if it's a sum variant, it converted into an OK of that type, or if it's a none variant, it converts it into an error. So if you have, let's say, an error of type 1 instead of 0, and I have a none here. You have 1, the 1 propagated back to the caller, right? Now map does something. So now let's say you have an OK of 2. Now map takes in a closure, right? This is a bit more advanced. It's basically a function, right? And it applies that to the contained value and returns it. So this will, sorry, so this will return 0. This will return 3. So you have OK of 2, which returned from here. It mapped 2 mapped to 2 plus 1, which became 3. And that 3 was added to the 0 from the first function and returned. So there you go. Okay, I've come to the end of this session here. So I've left out a lot of stuff in the, let's say, in the language, and that's purely because of time constraints. But here's sort of topics that if you wanted to explore further. There's the destructuring syntax where you can sort of access parts of an enum or a structure and then extract it while writing code or while doing variable assignment. You have if let and match statements, which are basically pattern matches, very powerful statements. You have traits. Traits are basically like interfaces, like and then you have lifetime, which is a bit more, let's say, a bit more in-depth topic. It deals with exactly how and when a reference becomes invalid, or when the references depend on each other for their activity or for their let's say lifetime. And you have the collection, the standard collection types, which you'll have in a lot of other languages. You have your maps, you have your lists, your vectors, and all. And yeah, that's it. I've come to the end here now, and that's sort of the session. I would say if there's any, let's say I'll open the session for any Q&A if there's any. Otherwise, I think we could leave. Uh, yeah, yeah. I don't see any question. I think we can close the session out. Yeah.